those two applications. It's actually a pretty good opportunity. So if you have any question, just ask him. Okay, he's very knowledgeable. Okay, maybe we can get started now.
Yeah, sure. Okay. Yeah. Thank you. Yeah. So thank you for inviting me here. And then my name is Chiu.
Sorry, we have a larger classroom.
It's okay. And then
Sit here.
so I actually from the engineering department, I'm kind of doing a lot of the research in the machine learning and the data mining, but the more applied side. And so applying the manufacturing and then some service science, and then so we got some interesting data, and then so hopefully after this seminar we hopefully discuss and then possibly some work together. And so today's what I'm going to talk is pretty similar to what I presented in I believe the last year in the statistical seminar. And there I presented how I scaling the computation of the Gaussian process regression or stochastic kriging. And I presented one topic there, but we had a new paper comes out, and then so this is the kind of follow-up work and then related to what I presented the last year. So this work is I co-work with Daniel Appley in the Northwestern. He's also in the engineering department, but he's working on some high number of statistical problems. So this is the organization of my talk, and then so pretty much is the 1 hour talk. And then so first of all is I introduced what is the issue and the big data issue in the Gaussian process regression. So here's the GP means just the Gaussian process. Okay? And then so after that is I discussed some existing approach. And then also I presented our approach, and then so which is called the patchwork kriging. And then so we have some numerical example with the reference. And so what I'm presenting today is just about some big data issue in the Gaussian process regressions. And then, but anyway, I'm not sure if you have some background in the Gaussian process or the Gaussian process regression. So I prepare some tutorial about the Gaussian process. Right after that is I presenting something about our approach. So basically, our motivation is this. Okay, we have some regression problem with a very large data set, and then we like to use the like the more Bayesian, non-parametric. One of the popular is the Gaussian process regression, and then so we want to apply this, but this Gaussian process regression has some computation issue for the large volume of data, and that's how we deal with this computation issue. That's the major topic of this talk. And then so our potential application of the Gaussian process is the three things. Okay, I understand is the Gaussian process is quite widely utilized in the spatial statistics, geospatial statistics, and then also in the general regression in the machine learning. But from the engineering viewpoint, we have the three applications. One is the simulation method modeling. Okay, we have some physical problems, but sometimes we cannot observe the physical problem because of the length scales of the physical problem, and then so also the time scale of the physical problem. For example, in the very small scale of the material is that you cannot observe with the sensors, even with the very state-of-the-art sensor, you cannot see the very fine scale of the length scales, okay, in the material behaviors. Also, even you have some electron microscopes and for looking at the very fine scale of the physical materials, and then so you cannot only capture the one snapshot of the material, you cannot capture the dynamics. And then so for those situations, what people do is using some computer models mimicking the real systems because there's no data. And then so what we can do is just using the computer model and generating data from the computer model. The certainly is we can generate many data, but that is very time consuming. What people do is just learning simulation by number of points from the design of experiments. They are kind of interpolating. Those are the output of the simulations, and then kind of mimicking the response of the simulation. That is called the simulation method modeling. So the other application is the uncertainty quantification. We have a lot of the stochastic processes in the real practice, and then so like to quantify the uncertainty there. And then so this is another problem that we are looking at. The last one is a sensor network, and then related with like a remote sensor from the satellite. And we have a collectively large number of observations, but that's still that data does not cover all the space of the measurements. And then so what you do is the interpolation with a large data set. Those are applications we are interested in. So just briefly is to introduce what is the Gaussian process, and then so how this is can be utilized for the regression problems. Okay. So Gaussian process by definition is the stochastic process. Okay, it's a continuous value. Okay, it's the real value stochastic process. It's the Gaussian process. If the it's a finite dimensional distribution is the Gaussian multivariate norm. Okay, and then so that Gaussian process is characterized by the two functions. One is the mean function that is pretty much characterized the mean of this stochastic process, and the covariance is like explaining the correlations. Okay. So Gaussian process is if you have one function f is realized from the Gaussian process, which means the f is the sample from the Gaussian process. If you take any finite number of the index of this stochastic process, you have that joint distribution is the multivariate normal. Okay, so mean of the multivariate normal and the covariance matrix of this multivariate normal is determined by this mean function and the covariance function based on the distribution. So that's basically the definition of the Gaussian process. So this, like the stochastic process, is a realization of the Gaussian process is the function of the index set. Okay, x is a function of x. Okay, and then it's then ranging in the index set x. So then is the Gaussian process is the kind of utilized for to define some probability space over the functions. Okay, and so because this is some randomness, and the output is the function, but that function response is the realization of the random process. Okay, so then the Gaussian process is the kind of defining some probability space over the functional space. Okay. So this is the one example, and then so suppose you have take the random samples from the Gaussian process. Mean function is the zero mean. Okay, so throughout you have some zero mean, and then so you have the covariance matrix this is the so-called the exponential covariance function because internal you have just the difference of the two input index set of the stochastic process. And then, so difference is to explain the correlation of the two measurements from the two different locations. Okay. So this length scales R, that's the parameter. Okay, and then this determines the kind of what kind of function you can sample from the process. Okay. For example, in the R is the 1/2 is the small value, and your function is pretty much the very low functions because covariance range is the small, which means correlation between the two neighboring locations is pretty weak. Okay, and then so you do not have any much correlation between the long length scales over the input, and then but if you have a large R, you have the much more smoother function because correlation is much stronger. So anyway, basically what I'm trying to say is that actually this covariance function, choice of the covariance function, determine your functional space and what is going to be the function you like to into. Okay, so then this is the kind of utilizing the Bayesian setting for the non-parametric Bayesian in the regressions. So what people do is in the regression is anyway you try to find some function, unknown function. Okay, and then from some training data, and the prior is the function we try to estimate that is a sample from the Gaussian process. Okay, so that defines the prior probability of this function. Okay. So typically, the m is defined as the 0, and then if that is the 0, this is the so-called simple kriging. M is not constant, that's the ordinary kriging, and then there are some other terms. Okay, and anyway, so we have the m is typically defined as a 0 in the machine learning, and but the other settings, the m can be defined using some priors. And the covariance is also defined some structures, is the shape of the functions. Okay, for example, in the smoothness is controlled by the length scale of the covariance function, right? And then also, if your function is the periodic, and you can define that this covariance function is the periodic function, you can define some periodic function based on this Gaussian process. Okay. So anyway, if you define this functional space and based on the Gaussian process with the training data set, and then some noisy observation from the stochastic process, and then you can get some positive distribution that is pretty much the Gaussian process duration. So it's a non-parametrics, and then so you do not have much actually. So the parameters, you have so many parameters. This is parametrics, and this is a Bayesian because you have the space of the non-parametric, and then so defined by the stochastic process. Any questions so far?
I have a question. Have you guys learned anything like stochastic calculus? But you do know like some process, Gaussian process, right?
Yeah.
Okay, very
Okay.
good. It's a shame actually. I mean, yearly SDE, I mean, all this stuff actually should
Okay.
be required
Okay.
PhD student in statistics.
So then is majority is the know about the Gaussian process.
So they do know
Okay.
Gaussian process, so it's
Okay.
good. It's very useful. Okay, in finance, for example, it's very actually in mathematical, financial mathematics, I believe, it's probably required.
Okay.
But the only difference, actually, the underlying mechanism here is continuous. It's a process. Of course, you observe discrete observations. That's the same.
Right. And then
Find a place.
so I believe is if you're talking about the non-parametric equation is pretty much is from the engineering side, and then we use the Gaussian process for the regression and then classification, and then also clustering, and then we have so clustering and then some other things, and then we have the Dirichlet process that's quite utilized a lot. And then also Poisson process is basically the counting process, right? And that's and those are we also quite utilize those and in the real problems. So anyway, just how we get the posterior belief is just to get the response is the y boldface, that's the vector values. So that's the collectively at all the response from the training data as a vector, column vector. And then you also have the location of the predictors, is the value of the predictor, that is the collectively you say is the x. Okay. So here's the axis is a vector, okay, I just abused the notation. Here's the axis can be it's like a row vectors. This is the kind of the column vectors, and then so you can just append those column vector along to the column size, and then so you can take a transpose that's just x, okay, and then also we have some f star that's actually what we try to infer, and then which is the f x star that is actually prediction at the unseen location x star. Okay. And the base pair using some Gaussian process, we can have the joint distribution very easily, and then so f star, and then so all training data with related, and then so with some covariance functions we define mean functions, and we have the multivariate normal distribution jointly. That's from the definition of the Gaussian process. So then it's just the Gaussian conditioning formula. You can have the posterior belief easily, and then so this is just one example of the prior Gaussian process, and then so after the observations, okay, how the Gaussian process is changing. So this is a prior Gaussian process from this exponential covariance, okay, zero mean. Okay, so this line is the mean function, and then so this shade is the kind of 1.5 plus minus the variance around your mean, okay, and then this is the random samples, okay? And then so as you can see, it's before the data is observed, and so the function is the very just around actually zero mean, okay. But suppose you have the 2 points observation noiseless, and then so your Gaussian process is updated with these 2 points, and then your covariance is the kind of saturated, and then so around the observation points, and then so if your location of the prediction is going further from that observations, the variation is the kind of increasing, which means the uncertainty of the predictions of this location from the far from the training point is the kind of large. Okay, so then is this posterior variance after the observation is the kind of quantifying the uncertainty about your predictions, and your mean prediction of the posterior mean is the kind of predicting the actual your point-wise predictions. So then this is kind of just interpolating the two observations actually, that mean function, and then you have some samples around that mean functions. So that's actually pretty much is just how you understand this Gaussian process, okay? And that's if you keep having some observation, your posterior is to keep updated, your uncertainty is to keep updated, okay? So now it's actually I'm discussing about some big data problem in the Gaussian process, and then so surely the Gaussian process is very easy to infer, and then just so like using some just multivariate normal, and then applying some Gaussian conditioning formula, you can have the closed form and the posterior distributions. That's very easy. Okay, there's no difficult. Okay, and then if you are talking about the computing. For the very large size of data, and then so the problem is the coming out, and then so for example, and then so in order to evaluate this mean and then posterior variance, okay, for each point, you need to do two steps of computation. One major part of the computation is the inverse of this big matrix. Okay. So if your n is the very large, okay, this matrix is the kind of the sample covariance matrix for the training data. That's the n times n. Okay, inverting that is the pretty expensive. Okay, so for the small size n, it's okay, just inverting just directly. But if n is the so large and the inverting that is the very expensive. Okay, so that's actually what we call this training time complexity. And then because this is the just happening the once with the training data set. But once you have the training stage is gone, and then so each testing point, you need to do some additional computations, and then that testing time complexity is the n square, okay? So this is certainly is the reasonable complexity for the small n, but the n is so large, and then so this can be very expensive, okay? So anyway, this is some computation issue in the Gaussian process relation. So it's what we're trying to do in this talk, in my research, is that we try to interested in the developing some approximate computation the algorithm for the scaling this Gaussian process is so better works for the large size of the n. Okay? And then so typically in the simulation method modeling is that we have a large scale of the design of experiments, and then so just pushing out the many data set, we need to interpolate. Okay. And the uncertainty quantification is the same, and then line as this simulation method modeling, how we quantify the uncertainty into this simulation output, combined with some very few experimental input. And the sensor network is these days number of sensor distributed is really large, and then so how you actually interpolate for some useful prediction in some unobserved location. That's the interesting.
Sorry, can you go back to the last slide? You said the computational cost is due to the sigma square I plus CSX inverse, right?
Yes. Oh, okay. So you mean, okay, so this is should be C. So it's a typo. This is typo, sorry. I used to use the capital K, but now I change it.
Okay.
Yeah.
Okay, another.
Yeah.
I forgot the form of this K or C. Is it possible to apply some sort of matrix inversion formula or do some pre-computation to simplify computation?
So certainly it's actually there are the multiple issues. Actually the n is so large, and then so this is the dense matrix actually. It's a very dense matrix. If you look at the typical covariance functions, so like this, right? And then so this is never going to be zero, right? It's always positive. So then your covariance matrix is the really dense matrix. So then just storing all the covariance value is the problems. Also the inverting it is the problem because that is not the sparse matrix. So any the form is typically is more looks like a banded matrix. Diagonal is really large, but that is the quickly saturating of diagonal terms, right? And then but still that is the non-zero. And then so you still have the non-zero.
The diagonally dominant feature in some sense.
Right.
So I'm thinking maybe you can use the structure to facilitate.
Yeah, that is actually the kind of what people do, and then so the kind of sparse approximations, and there's a kind of truncating out some the very small, close to zero values. Yeah, that is the so-called the tapering and the tapering matrix.
Yes. Okay.
Yeah. So anyway, I just review those approaches. Okay. Anyway, this is the complexity, and so we try to develop some of the approach. Okay. So some existing approach is just coming out here in the sparse approximation. So the major issue in the computation is the inversion of the large sample covariance matrix, and what people like to do is to kind of approximate that sample covariance from the matrix as some more easily invertible form in terms of computation. So the one way of doing that is approximating the covariance dense matrix with some sparse version. After that, they can utilize some sparse computation technique in the matrix, and then so linear algebra, and then that's the one thing. And then so one popular technique in the statistics is the covariance tapering, and so that idea is already pretty mature. And then so I just briefly mentioned here, and then this idea is if you have an original covariance here, and you multiply this covariance with another positive definite corners, okay, which is taper function. Okay. So this taper function is making some very close to zero values, and then in the covariance is equal to zero. Okay, and then still maintaining the positive definites, because you have the two positive definite function. Product of that is the still positive definite, and then this is the still valid covariance function. And then so resulting the central covariance matrix is the still positive definite, and then this is the one way of the truncating. Okay, so this is the one idea. And then so one of the good aspect of this covariance tapering is that this is the kind of asymptotically truth for some specific covariance function. For example, in the Meton covariance function, that is kind of the popular choice in the. So this covariance tapering is the asymptotically approximating the full Gaussian process. Okay, and then so for some specific covariance function like Meton. Okay, and then so some similar result is achieved by the Gaussian Markov random field approximation of the Gaussian process. Okay. So the difference of the Gaussian Markov random field is actually you have a precision matrix is very sparse. Okay. So because of the Markov properties in the field, and then so you have some conditional independence, and then so all the precision matrix corresponding to the independence in the conditional, and that is all zero in the Markov random field. And then so then the inverting that the sparse matrix is pretty easy in the computation compared to the actually Gaussian process. That's another approach. Okay, this is actually Harvard Lu's approach, and so he actually worked on the Gaussian Markov random field a lot, and then so he kind of linked the stochastic differential equation solution to actually Gaussian Markov random field, and then so how the solution of the stochastic differential equation can be approximate the Gaussian Markov random field. He make a link, and then so some specific Meton covariance, and then the Gaussian process with the Meton covariance can be expressed as a solution of the stochastic differential equation. Then that solution of the stochastic differential equation can be approximated the Gaussian Markov random field. Then for the Meton covariance is the Gaussian Markov random field approximation is the kind of asymptotically true, and then those are already proved in the paper. Okay, and that's actually the two main line of the paper. So another research is using some compactly supported covariance, and then this approach is somewhat similar to the covariance tapering, but this is not very general because you need to use some specific definition of the covariance functions, which is so-called the CS covariance functions. But here's the tapering is more general because if you have any covariance function, you can taper, right? But this is the choice of the covariance function is limited to very few choices if you use this. Okay? But anyway, yeah, that's what this is the.
So these are largely related to what we learned, right? I mean, like concentration matrix learning, and I mean a lot of things. Although these names are not familiar, this literature are not familiar to us, but of course, it's a discrete setting. But we actually also have the same things. We want to capture the sparsity pattern.
Okay.
I mean, on the concentration of those matrix. And there are different types of structures you can assume, and you can also use tapering.
So then is the concentration matrix is the symmetric symmetric matrix?
Yeah, symmetric.
Okay, symmetric.
Symmetric, but you don't really assume where the zeros are. You don't even assume it's diagonal.
Okay.
Like decaying structure.
Okay.
There's a large volume literature.
Okay.
Yeah, we usually call it like covariance estimation, non-Gaussian. Actually we can do non-Gaussian as well.
Okay.
But usually you call it covariance, but you actually would go back to the precision of concentration matrix. But this literature, these papers are in what areas actually?
So those are two topics is from the statistics. I believe that this paper is in the JRSSB.
Oh, okay.
And then so this paper is also JRSSB, and that's in the 2011. And so this is a very excellent paper.
Okay. I recognize any names.
Yeah, so you can look at. So this is the Harvard rules, and then so this is the I forgot. It's the so that is on my lessons list. And then so Fuller.
Ah, okay, Janet. Okay.
Yeah. Yeah. The
Okay.
Fuller Ganton, and then Ichika is the kind of famous person, right?
Yeah.
So Mark Ganton in the now A&M, Texas A&M staff, right? And
Okay.
so the Lindgren, this one, Harvard rule, this is the Markov random field. And then so approximation of the Gaussian Markov random field to the Gaussian process. And then so that is from the linkage between some stochastic differential equation to the Markov random
Your
field.
paper with Jianhua.
Yeah. This is what I presented the last year, but we have a follow-up paper. This is a follow-up paper. And then so, yeah. Yeah, just please tell me anytime if you want any questions.
Excuse me.
So-
question.
Yes.
May I ask why you need a sparse approximation?
So reason why that is the computation is because if you have a sparse matrix, so inversion of the sparse matrix is much efficient than just the inversion of the full matrix. Because think about your inversion. So when you invert, and the typical how you do is you take the Cholesky decomposition. If the matrix is the positive definite, you can take the Cholesky decomposition, and then that Cholesky decomposition of the sparse matrix is also sparse. So once you have the sparse Cholesky, and then so taking the Gaussian elimination for having the solution is efficient because many of the entries are zero, and the Gaussian elimination steps are much less than the inverting the full matrix, right? So that is the kind of the computation technique in the sparse matrix. So how you invert that. So the choice the computation reduction is depending on the how sparse is the matrix. So that is depending on the choice of the R. If the range of the R is narrow and your matrix is more sparse, more so along to the your diagonal part of your matrix, and then it's just a few off diagonals to non-zero, and then all the others are zero, right? So another approach is the low rank approximation, and then this is the kind of based on some latent variables, and then so people are talking about the latent variable in the many other the machine learning approach, and then so they introduce some very small number of latent variables, and then so allow actually that this latent variable is correlated with the observed variables, and then the number of the latent variables is much smaller than the real variable. Then is if you have some independence conditioning on this latent variable among your observation, you have the low rank version of the covariance matrix, and the rank is determined by the number of the latent variables. Okay. Then the complexity is reduced if you have a low rank version of the matrix, and then so inversion of that low rank version of the matrix is reduced by the m squares. Here is the n is the number of data, m is the rank of the matrix. So typically it's the rank, and so you have the n squared, right? Then so your computation for the full version is the n cubed, right? Like just the full inversions. But if you have some reduced rank approximation, and then so you have a lot reduced complexity, and for the training, and then also the testing side for each testing point. Okay. So that's the basic idea. This is the kind of popular approach in the machine learning. Lots of the paper published it. It's around 2006 already, and then so still in the recently there are some publication, but those are pretty just a small variant of the existing approach. Some phenomenal work is the Snelson's work, and then he graduated from the University College London, and then so now I believe he's in the Microsoft Cambridge, and then so some leading some machine learning department, and then also TTS is the kind of proposing something similar, and so some other phenomenal work is to propose along to this low rank approximation. So there are some variants, but the major idea is this: just introduce the latent variable, small number, and then so using some correlation between the latent variables and then your actual observations, and then you can reduce the length of your sample covariance matrix. Okay, and then so pretty much you reduce the length of the covariance matrix.
So this is like, I mean, what we learn in covariance estimation, how this works. You know.
Okay, okay. So very relevant then.
But now people usually
Yeah.
tend to combine these two,
Okay.
like
Okay.
latent variable, product selection, and we learn